Hey there! Nice to see you all again. Hope you had a wonderful Thanksgiving break. Now it's time to get into some bonding. Those atoms making connections. And some naming. So you're going to learn the language of chemistry. Your mom is going to be so proud when you can read the cereal box and actually know what's in those ingredients. Just wait. Alright, so to start out, we're going to look at where the electrons are. So this is kind of coming from our last discussions on electron configuration. In order to know what those electrons are doing, we need to know where they're at. So let's take a minute, review a little. If we have these elements, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, it's like a song, what would be the electron configuration? Well, if you check your charts, we know that lithium is a 1s2, 2s, 1. Beryllium, 1s2, 2s2. Boron, 1s2, 2s2, 2p1. And all of these are going to have the 1s, so I'm just going to put some repeat signs there. They're all going to have the 2s, so I'm going to put some repeat signs there as well, just to save some time. And our carbon, 2p2, nitrogen, 2p3, 2p4, 2p5, and 2p6. Okay, hopefully you remember these from our last chapter. Okay, so now that we know where all the electrons are, let's take a look at the outermost energy level. This is what we call the valence energy level, or the outermost. So if we take a look at lithium, our outermost energy level is the second energy level. Same with beryllium, same with boron, same with carbon, and so on. Which makes sense because they're all in the same row. So that means they're all the same energy level. Well, we like to look at that outermost energy level, but what's really important are those electrons. So how many electrons are in that outermost energy level? That was our valence energy level, so that means that these are going to be our valence electrons. So if we take a look at lithium, in the outermost energy level, there's 1 electron. In beryllium, there's 2 electrons. Boron, we have a 2s and a 2p. They're both the outside energy levels, so we have 3 electrons. Are you seeing the trend? Carbon has 4, nitrogen has 5, oxygen 6, fluorine 7, and neon 8. So as we go across the periodic table, there's 1 more electron in that outermost shell, all the way up to 8. If we were to then go to the next row, to sodium, magnesium, we'd start over again, because that starts in the third energy level. All of these electrons are the valence electrons. This is going to be very important, the outermost electrons. So if you take a look at how that worked in our periodic table, everything in this first row is going to have 1 valence electron, 2, 3, 4, 5, 6, 7, and 8. Except for helium, it's a little guy, it only has 2. So remember that in our D and our F blocks, it goes down energy levels. That's the third, will be in the 4th energy level here, but this goes to the 3rd. So this isn't going to ever be the valence. This is always going to be one energy level further out. So those are going to be our valence ones. D and F blocks don't really matter at this point. So valence shell, outermost electrons. Outermost electron shell. The valence electrons are the electrons located in that outermost shell. These are the important ones. These are the ones that we're going to be paying attention to from here on out, because these are the ones that are involved in bonding, the coming together of the atoms. All the others that are still in there are called the core electrons. Now we still know where those are at. We know what energy levels they're in. We know what shapes they're flying around and what orbitals. But pretty much from now on, these are just hanging out, being eye candy for the protons. They're just there to keep the protons happy. It's those outermost valence electrons that are the key. So when we're talking about ions, remember that atoms and molecules have gained or lost electrons. That's what an ion is. And why do they do this, you might ask yourself? We talk a lot about ions, but why would they ever want to do that? Well, one of the answers is for chemical stability. Remember that electrons are the ones involved in bonding, and bonding helps chemicals be stable. So, by gaining or losing electrons, they can bond and become stable. But the real reason is they have a little bit of noble gas envy. Remember, the noble gases are the kings of the periodic table. They are the cool kids on the chart. Everybody wants to be a noble gas. And noble gases have 8 electrons in their valence, or an octet, except for helium, because remember, he's a little guy, he has 2 electrons. So this is what we call the octet rule, is that all atoms want to have 8 electrons in their valence, just like the noble gases. They want to be like those cool kids. So the octet rule, oct means 8. Everything wants to have 8, and so they'll lose or gain electrons in order to look like these cool kids. But does the identity of the element change when it forms an ion? Will losing and gaining electrons do anything to what the element actually is? Well, you should say to yourself, self? Of course not. Protons never change, and protons give the identity. So as long as protons are staying the same, the element is still the same. Remember, we talked about 2 types of ions, cations and anions. Cations are the positively charged ones. They have lost electrons, and anions are negatively charged atoms or molecules, and they have gained electrons. So you might be thinking to yourself, well, what ions do the elements form? Well, this is really easy to figure out, actually. So if you think about the periodic table, over here are our noble gases. Remember, our noble gases have 8 electrons in their valence. They are happy. They don't want to lose. They don't want to gain, because they're the cool kids on the table. They are perfectly content with where they are at, sitting on their thrones over here on the noble gas column. This column right here, the halogens, are 1 away from having those 8 electrons. So they're going to form a 1 minus charge, because they want to gain 1 electron in order to look like those noble gases. This row, our oxygen family, is 2 away from looking like the noble gases. So they develop a 2 minus charge. They want to gain 2 electrons to look like those noble gases. Our nitrogen row is 3 away. They want to gain 3 electrons to look like those noble gases. Now the carbon row gets a little goofy, because if you notice, it's right in the middle of going this direction, or it could cheat and go backwards. So it could be a -4, it could gain 4 electrons, or it could lose 4 electrons and have a 4 plus charge. If it loses 4, it goes backwards until it will look like helium. If it gains 4, it looks like neon. So it has some choices. As we keep working our way across, these guys are kind of the cheaters here. They don't want to gain electrons. It's more work. They don't want to do more work. Kind of like everybody else in this world. You do what you got to do. So it's a lot easier for it to lose 3, 1, 2, 3, and go backwards than it is to gain 5. So here is where our plus charges start. These elements will form plus charges, +3. These are 2 away from becoming noble, but they have to lose those 2 to go backwards. So they form a 2 plus charge. And this row forms a 1 plus charge. If it loses 1 electron, it looks noble. Notice that hydrogen is on here twice. Hydrogen's kind of a goofy element. It can fit in either place. So sometimes it's a plus, sometimes it's a minus. You never know. So when these ions come together right now, form an ionic bond, yeah. Okay, these ions come together. It's a bond formed between 2 ions by the transfer of electrons and charge attraction. Okay, the elements that want the electrons are going to steal them, and then there's going to be charges, and opposites attract. This is kind of like one big greedy dog thief. Okay, and remember, it all has to do with something called electronegativity. If you remember what that term is, the ability to attract electrons. The element that more easily attracts electrons is going to steal those electrons from the other, become charged, and then they're attracted. Okay, so this big greedy dog thief is like the electronegative elements, the ones that want the electrons. This other one doesn't want the electrons as much, but it'll be attracted to that negative charge. Okay, so the electron is stolen by the more electronegative one. They become charged and attracted. So, when charges attract, you get an ionic bond. Electrons are stolen or transferred, you get the ionic bond. This happens between metals and nonmetals. Opposites attract. So remember on your periodic table, we have that stair-step line that separates our metals and our nonmetals. Remember that these are our metals and these are our nonmetals. So you always have to think one from this side and one from this side. When they bond, it's an ionic bond. When those elements bond, when they come together, their goal is to get a 0 overall charge. So you want all the positives to cancel out all the negatives. So for example, NaCl. Na has a charge of 1 plus. Here it is. Cl has a charge of 1 minus. So 1 plus and a 1 minus, you need one of each to cancel each other out. When you're writing these formulas, cations, or the positive ones, will always go first. We're always positive before we're negative. Positivity first. Anions are negative, they go second in the formula. The number of atoms is going to be in the subscript. So sub means below, like submarines go below the ocean. So for example, Sr has a 2 plus charge, chlorine has a 1 minus charge. So in order to get these to balance out, we'll need 2 chlorines. So this 2 down here is our subscript, and it tells us how many we need. If we have 2 negative charges and a 2 positive charge, they cancel each other out, and an overall charge of 0. If there's only one atom, you put nothing in the subscript. So here, there's nothing. We just assume that it's 1. All ionic compounds are salts. We talked about this a little bit earlier when we did some flame tests, but whenever you have these charges attracting and bonding, all of those are known as salts. So let's give it a go. We have a cation here of lithium. If you take a look at your periodic table, you know that it is in the first row here, right here. So it has a 1 plus charge. Fluorine, right here, has a 1 minus charge. So if these are going to bond, a 1 plus and a 1 minus, we get LiF, because we need one of each. They automatically cancel each other out. So LiF. Let's try another. Magnesium. Magnesium, if we find it on the periodic table, has a 2 plus charge, just in the second column. And chlorine, over here, has a 1 minus charge. So a 2 plus and a 1 minus. So in order to get these to balance out, we need 2 of these. Now remember, when we have multiple atoms, it goes in the subscript below. So we need 1 magnesium and we need 2 chlorines. So MgCl2. 2 of these equals a 2 minus and a 2 plus, cancel each other out. Now let's try this one. This one gets a little tricky. Sr, here it is on the periodic table, right here. So it is a 2 plus. And nitrogen, over here on the periodic table, is a 3 minus. Now notice all these are, the cations are the metals, and the anions are the nonmetals. All of our ionic bonds are between those two. Alright, so this one's a little tricky. We have a 2 plus and a 3 minus. How do we get those to equal? We can't just multiply one of them, but we can find a common factor. So if we look between the common factor of a 2 plus and a 3 minus, our common factor is 6. So in order to get a 6 charge on this one, we'll need 3 of them. 3 2 pluses equals a 6 plus. In order to get 6 here, we need 2 of them. 2 3 minuses equals a 6 minus. So SR3N2. practice this a little bit more a little later on, and we will